Hello, I'm Anna Mackay and this video is on inflections and shape. This Venn diagram here is actually quite handy to be able to compare the differences and the similarities between stationary points and inflection points. So you can see that there are stationary points here which are local max or minimums, and these ones over here where you would have a stationary point, so your tangent there would have a slope of 0, but they also double up as a change of shape, going from concave to convex or concave up to concave down, etc. Whereas these ones over here are inflection points, but they are non-stationary. And what we mean by non-stationary is they're not stopped. They're on the move, if you like. So this one goes from concave down to concave up in one swift motion without a horizontal tangent, without pausing, or the vice versa. So when we come to classify stationary points and inflection points, sometimes there's a double up. So come back to this one if you need it. These charts might be handy too. My class, you'll get a copy of this. We're going to draw in the shape that matches these. So if the sign for our first derivative goes from positive to negative, that means we are increasing in our slope and then decreasing. So this is a maximum looking shape. And what is the shape of the curve then? It would be concave down. So the whole time. So negatives are sad, so it's got a sad shape. So that would correspond to this, with at the point A would be our stationary point. The flip side of this one, if we go from negative, so we're decreasing, and we stop at A, a stationary point, and turn, the second derivative would be positive the whole time, because that's concave up, which is positive, a smiley face, positives are happy, and so that's the shape that we would get. So because we're going to do some questions where we draw sign diagrams for both the derivative and the second derivative and compare them. The next two, they would look like this. So if we are going decreasing to decreasing with a stationary point at A, what would that look like? You're going downhill, pause at A, and then downhill again. And so the shape that corresponds to that is this, very roughly drawn there at A. Now, in terms of it is a change of shape. You think about this, if you were to continue this curve and didn't stop at A but kept going back up again, you could see that that's part of a smiley face, if you like. Smiling is happy. So this first part is positive, a positive shape, and so therefore on our sign diagram for the second derivative, it's a positive value. And then after A, it's downhill and it's part of a negative shape. It's a sad face, so hence the negative here. The reverse of this one, but similar, is going the other way. A stationary point at A and also a point of inflection, a change of shape there. And then the last two are the non-stationary inflection points. So it changes shape, but it doesn't stop, so to speak. It doesn't have a stationary point. And those ones look like this, with the change of shape happening there at A, but not stationary points. In this case, they would happen at B and C. And there's lots of information in this table here that might be of use to you. And the reverse of that is going this way. So A is our change of shape, but it's not a stationary point at the same time. So think about these tables from time to time, handy to have on your formula sheets too. All right, a couple of examples. If we have to find and classify all points of inflection of this quartic. So first of all, differentiate. So our derivative for this is 12x cubed minus 48x squared plus 48x. Now, as I always say, see what that looks like first. Draw it in your graphics calculator. Create a visual. And it looks something like this. So you can see how many you might be expecting to have. How many stationary points at the most? 2 there. And we'll get into more detail later as to how that connects to the fact that it's a power of a cubic of 3, so it's a cubic. Then the second derivative, we have to differentiate again. We get 36x squared minus 96x plus 48. So first of all, to find the inflection points, we do need to do the stationary points as well, because sometimes they double up. So stationary points, therefore the first derivative is equal to 0. So I'm going to take that function and put it equal to 0. I'm going to get straight into some factorising. We've got a factor of 12 and an x. That leaves us with x squared, take 4x plus 4, and solving that when that's equal to 0. So leaving our 12, and you may hopefully recognise that that's a perfect square. And so our x values for our stationary points are at 0 and 2. For our second derivative, we have inflection points when the second derivative is equal to 0. So the second derivative tells us about shape. Now I'm putting this function equal to 0 and solving for x. Straight into factorising out a factor of 12 there. We're left with 3x. Take, what have I done there? 3x squared, take 8x plus 4 is equal to 0. And now we have to factorise that. Feel free to use your graphics calculators. Your A and your C gives you 12. Another way to do these ones though is split those terms to multiply to give us the positive 4. We would probably need a negative 2 and a negative 2, and the cross multiplying works there. Negative 6 subtract 2 gives us negative 8. So we have this, x take 2, there are factors, and solving for x, our values are 2 and 2/3. Now they're going to come in handy when we draw our sign diagrams now. So a really handy technique is to draw the sign diagrams one on top of each other, or above and below. So the first derivative and then the second derivative. You put on those critical values. So for the first derivative we had 0 and 2, and for the second derivative we also had 2, but also 2/3. Now if you've already got the graph of that, I'm just going to quickly draw it off to the side here again, we can help fill in the signs. You can substitute numbers into the functions to work these out as well, or you can read it off a diagram. So the first derivative talks about shape. So we're downhill till we get to 0. Downhill is negative, and then we are increasing uphill. We pause at 2, and then it's uphill again. And thinking about the shape, so this is about the concave or convex. When we start here, that's part of what type of shape? Well, a smiley face, and smiley faces are happy, so they're positive. Then where does it change? Somewhere in here, which would be our 2/3, and then the next portion, if you were to extend it out, would be part of a down curve, a concave down, and so that's negative there, and then it's positive after that. But we have to classify the points of inflection. So we have 2 points of inflection. One is stationary, one is non-stationary. So this one here is non-stationary, it's on the move. So we write non-stationary inflection, I'm just abbreviating that, and also a stationary inflection. But where? So you take this number 2/3 and substitute it into the function. Feel free to use your calculators for that. Both of them, the non-stationary one is at 2/3, and that comes out to be a decimal of 2.48, and the stationary one is at 2, and you substitute 2 into the function to get 7. And so if you were to look at the sign diagrams for these, if you look at that portion and look back at those tables that we've done, that would match a stationary inflection. And then if you look at the sign diagrams around this area for the other one, that would indicate the same as a non-stationary inflection. Okay, a couple more. So considering an exponential one this time. Find the x and y intercepts. So just a few things to point out here. If we have our y-intercept, we've got x is equal to 0. So substituting in 0 here, we get 0 plus 5e to the power of 0, which is 1. So we get 0, 5. Graph this to see what it looks like as well. How many intercepts are you expecting? Oh, that's very rough. Anywho, so our y-intercept is there. Any x-intercepts? No. And let's justify y. So we would have x-intercept therefore y is equal to 0. So we're trying to solve this algebraically. When is that equal to 0? We rearrange that to get, having a pause here, but anywho, 5e to the negative x is equal to negative x. Now, you might be having a think, when does that happen? If you were to imagine that as rewriting that with logs, you might be wondering, when is this ever true? And hopefully you know that ln x is always greater than 0, so therefore it can never be a negative, so therefore we actually have no x-intercepts, therefore no x-intercepts for that one, and that matches what we were expecting. Now, classifying any stationary points, so we have to differentiate. So differentiate this, differentiating x is 1, differentiating the e function, you copy and paste, and differentiate the power, so I'm going to jump straight into what the answer would be there. Now, stationary points at f dash x is equal to 0, so let's put that equal to 0 and try and solve. So you'd rearrange and see what you get. Now, we've got that. So we're trying to solve for x. There are two ways to do this now, and I'd like to show you both. If you've got x in the power, using log laws helps to bring it down out of the power. So you could log both sides, but doing a natural log, because we've got the e there, ln1. Now, we could split that log, if you like. You might think of it in a couple of different ways. Because there's two things being multiplied together there, you can use the addition law there. ln1 is 0. And then solving for x, this part becomes just negative x, rearranging ln5, and so therefore x is equal to ln5, because if we want the exact nature of them, of the stationary points. And the other way you could solve that, you might think of it, you might look at that and go, okay, I'm going to keep rearranging to that. Now, how do I get x down out of the power? I would log both sides with a natural log, ln, but I'm going to write that as 5 to the power of negative 1. So this log here, and simplifying this, and this part here, we can bring the negative down out the front. So then we get ln5 there, and as you know, this part here was equal to the negative x, simplifying, and you get there. So there are a couple of ways to go about that, depending which way your brain might see it first. And, I need to go back. So we need to classify the stationary points. So first of all, the point is at ln5, we need to substitute that in, and to the function. For time, I'm just going to speed this one up. So f of ln5 comes out to be, if you want to sit there and work it out exactly, it's ln5 plus 1, or that then comes out to be, as a decimal, 2.61. Feel free to check that on your graphics calculator when you substitute in ln5 and find the y function. Okay, and one more here, discussing infinity concepts. So as x heads towards negative infinity, so you need to think about where x is and what would happen as we head towards negative infinity. Now, remember, that's approximately what we're thinking of. The bit with the exponential, though, is going to be more affected by large numbers than plain x on its own. And so the way to set this out, as x heads towards negative infinity, you look at the component with that exponential, and you would say that part, what does that head towards? That's actually going to head towards, so we've got the double negative happening there, so that portion is heading towards positive infinity. Now, you might say though, yes, but this part is heading towards negative infinity. So if you have negative infinity plus positive infinity, don't they cancel out? Does it head towards 0 then? Well, no, because here we've got 5 multiplied by positive infinity. So this positive infinity part is actually going to counteract that negative infinity part. So that's the bit that's going to win out. So therefore we have y heads towards positive infinity. So as x heads towards all the negative numbers over here, y is increasing to positive infinity. Okay, the next video in this series is about the graphs of the different derivatives. Make sure you subscribe. Thanks.